Wait, I got one.
All right, so now that we're going for realsies here, we're going to pick up where we left off, which was, again, looking at waves. And we got to the point now where we saw the energy and power in a mechanical wave. We've talked about the two different kinds of waves, the transverse and the longitudinal. And remember that the difference there is whether or not the motion of the particle is perpendicular to the travel of the wave, right? Which one is that, transverse or longitudinal?
Transverse.
That one's the transverse. Yep. And then longitudinal is your motion is in the same direction as your oscillation is in the same direction as the motion of the wave. And so those are the longitudinal. And the really good examples, we'll talk a lot about this one. Sound, that's where we're going today. Sound is a longitudinal. It goes back and forth, as opposed to like light, which is transverse, or like a good old wave on a string and all that. Okay, so that's where we were, and we're going to pretty much just keep going on this. And the next thing I want to talk about is intensity. So when we talk about the intensity of a wave, that's specifically used a lot when we talk about sound, the intensity of a sound wave. You may know the unit decibel. So when they talk about loud noises and they talk about a decibel number, you know, like at a stadium or a rock concert, those are measuring their measurement of intensity, right? So that probably isn't going to surprise you that it's going to have to do something with the energy in a wave. If a wave is more energetic, it's going to have greater intensity. So in sound, we use decibels. With light, we use lumens. I don't know, or there's also, what's it, candles. It's another super old, antiquated unit of light intensity. But with waves, we're often interested with the intensity. I mean, we talked about earthquakes the other day, and the intensity of earthquakes, the Richter scale, that's partially a measure of the intensity of the wave. So we need to define that. We need to define what intensity means. So intensity is really easy. It's actually the amount of power over a given area. Okay, so greater intensity would mean if we picked a certain area, right? So we got like just this area right here. If we increased how much power was in this area, the power of all the waves that are in that, we would have greater intensity, or vice versa if we decrease the power. So it's actually super easy. It's just power divided by area. But here's what gets kind of interesting when we talk about waves. Now, let's say we're going to talk about, say, an earthquake. So an earthquake happens at one point inside the earth. When that happens, that shift of the plates or whatever creates a shock wave. And that wave starts leaving from this point in all directions, right? And that's one of the ways that we can actually figure out where earthquakes happen, is by having multiple sites that measure how long it took for that wave to get there, and then we can kind of triangulate back, right? So it goes in all directions, which means that that energy is propagating out in a sphere. So if we were to look at any particular time, right, we just take a picture real quick, right? Take a snapshot. If we could actually see the wave, that pulse as it leaves, we take a picture, it would look like a sphere. A little bit later, it would be a bigger sphere. A little bit later, still a bigger sphere, because the radius is going to be increasing at whatever the speed of the wave is. Okay, so think about that then. Whatever power that wave has is going to be the same whether it's on this small sphere, this bigger sphere, this huge sphere. It's always going to be the same. So as time goes on, as this wave travels further, the intensity dies out. Now, that's not just true with earthquakes. I mean, obviously, we know that's true because, say, there's an earthquake in Chile. Remember that huge one in Chile about like 5 or 6 years
I
ago?
was in there. I was there.
Were you there, Max?
It was
Bad?
crazy.
How bad
It
was
was
it?
very
Because
good.
it was big, right? Wasn't it an eight something? I
Yeah, it
think.
was like 8.3.
Yeah. So that was pretty monstrous. But so I was just about to say, so when that thing happened, none of us felt it. Well, that's not true because evidently Max felt it. Um, but
Yeah.
I doubt that the rest of us felt it. I know I certainly didn't because we, here in Tahoe, we're far enough away that the energy had really kind of dissipated as time went on, right? We see the same thing with light. Think about it. If you've got, say, a light, just a good old classic light bulb, hanging here, it's super bright near it, and as you go further away, it gets darker, right? We know this. We know we have to be, at a certain distance in order to still be able to see. And sound does the same thing. If we were all in the same room, you could hear me just fine. But then if you went down the hall, you'd have a harder time hearing me because the energy dies off, right? So we already know this. We already know that the intensity is going to decrease. But what gets a little bit crazy is that this intensity actually decreases with not just distance, but the square of distance. So let me show you what I'm talking about. And while I'm switching here, I'm just curious. So Max, where in Chile were you?
So I was like, because we used to live in the south, and I was in a town called Nyankul, and it was really close to Pucón. That was like a tourist place.
Yep,
I don't know if you know.
I know Pucón. I'm contemplating going down in December because there's going
Yeah.
to be a total eclipse of the sun.
Oh, really? There?
Yeah,
Oh,
it's going
that's
to
really cool.
slice through Chile and Argentina, and
Wow.
I know that Pucón is like right in the middle of the strip. So I actually
I
have a rental place just in case, but with all this COVID stuff, I don't know that I want to leave the country because I
yeah
may not be able to get back. I mean, I've
yeah.
seen that
I-
Pucón is like super beautiful, like very much like Tahoe, so might not be the worst place to live, but it's not home. Anyway,
Yeah.
so
I lived like 2 hours away from it, I think, and I mean, when it happened, I remember like it was crazy. I was having a dream that there was like a big machine moving my house up and down. Then I wake up, and sure enough, it was just an earthquake.
wow,
Just an earthquake.
yeah, just an earthquake, no big deal. All right, well, so where I was getting with this is if we look at the intensity, it's power per area.
I'm sorry to interrupt you, but
Yeah,
I
go
just
ahead.
thought of something.
Sure.
You know how you said earthquakes can either be longitudinal or transversal? Does that dictate whether or not a tsunami will happen if it's, say, in the ocean?
I don't actually know if one is more likely to cause a tsunami versus the other. I really don't.
You think Scott would know?
He might. I know that. I was going to say, I know a lot of times those are caused by like landslides that happen. So it's not necessarily the wave itself, the earthquake wave itself, but a shift in the earth. So yeah, I don't know. That would definitely be a question that I asked Scott Valentine because he would definitely have a better chance of knowing than I.
Okay. It just made me, I don't know, was just curious.
So let's think about this. Here's the sphere. So let's say the center is where the wave started. And of course, we're getting a sphere of radius r. So all of that power is spread out on that surface area. So does anybody know the surface area of the sphere? Anyone know the formula for that? It's okay if you don't. I was just curious.
I don't.
It's actually 4 pi r squared.
Yeah.
If you want a way of knowing how to find that, check this out. If you know the volume, this is an aside, but volume is 4/3 pi r cubed.
Ooh, they
Check
get
it
over
out.
this next.
Differentiate that. If you differentiate that with respect to r,
Well,
you get 4 pi r squared.
Volume goes into area.
Right? So even better, if you look at an area of a circle, suppose you differentiated that with respect to r, you get 2 pi r. Remember what that is?
circumference.
It's your circumference.
And so if you
So-
integrate it the other way, you get the opposite.
Yep. So there's definitely a relationship here with the circular stuff. It is not coincidence, but it doesn't hold true for all shapes. So just be aware. Anyway, I digress.
That's wild, honestly.
Yeah, it is. This
Yeah,
is pretty
it's
cool. That's the mathematician in me coming out. All right. Well, anyway, so here's your surface area, which means this intensity then, it's going to be whatever our power was. If we know the power of this thing, we end up dividing it by 4 pi r squared. And so here you can see how this is inversely proportional with the square of r. It dies out with the square of r. So if you double your distance away, the intensity drops by a factor of 4. If you increase your distance away by a factor of 10, the intensity is 1/100th of what it was.
That blows my mind with how bright some stars have to be.
Oh, yes. Yeah. When we see stars that are really bright, like Sirius or Vega or things like that, they're really far away, and yet we still get quite a bit of light. Now, it doesn't even come close to like the sun, but we're obviously way closer to the sun than other things. So the fact that we can see stars at all means that they are emitting a ton of energy, right? Just massive amounts of energy so that that power is great enough so that we can see it. Well, you remember gravity? The formula for gravity had an r squared in the bottom.
Yeah.
It's really kind of the same idea. I mean, we didn't talk about it back then, but if we were going to look at gravity as, well, we've got this source of gravity, the center of the sun or something. As you move away, all of the energy that gravity has to pull you in is getting split amongst a sphere. And so as you move away, when you're on that bigger sphere, every point on that bigger sphere has to experience the same gravity. So we're actually dividing out by an r squared. So there are lots of things that actually follow an inverse square law. That's what we call this. It's an inverse because it's in the bottom, and then square. So it's an inverse square law. So you'll see light does this. Magnets, so magnetism, the strength of magnets depends on distance away, and it's inverse square. Same thing with electrical charge, electrical attraction.
Isn't it a similar thing with gravity too?
Yep.
Yeah.
Yeah. So all forces that are what we call field forces, which are ones that don't require actual contact, like gravity, magnetism, electricity, all of those follow inverse square law. All right, so this is how you'd actually measure the intensity. And so when, for example, we're going to talk about a decibel level, sound intensity, it totally depends where we are. And if you've ever been to a concert, you know that that's true. If you're up closer to the speakers, it's much more intense sound, right? Your eardrums start bleeding, as opposed to if you're further away, right? But we definitely have that fact. All right, so energy leads to power, power leads to intensity, and intensity is usually more what we're concerned about because we want to know at this one location how much energy is coming. So, all right, well, let's keep talking about waves moving, because when we were talking about speed and energy and all that, it's all about motion. But I want to talk about what happens with waves when there's a reflection. So let's go back to the good old string. So I'm going to be looking at a wave on a string. And let's say that we've got like a post that this wave is attached to, or the string is attached to, right? So here's our string that's attached to a post. So we're going to send a pulse down this way, or down this string. So let's say that this pulse starts like this. Okay, so there's our pulse. So we just took that string and we, flicked it like that. So we send this pulse, and this pulse is moving down. All right, so a little bit later, that pulse is going to be closer to the end of this, right? So now it's just about there. And so the question is, what happens once it hits that post? Well, you can actually observe this. If we were in class, I would try to show you a demonstration, but I'm not even going to attempt to do it in here. But what you see is after reflection, it turns out that that pulse is upside down. So upon reflection, it gets turned upside down. All right, so then the question is, how fast is it going? And what do you think? Is it going to be the same velocity coming back as it was going in?
I think that depends.
Depends on what?
If we assume conservation of energy or not, or if we lose some.
Okay, and that's exactly it. In the perfect world of ignore friction and all that other good stuff, then it would come back in exactly the same shape, just upside down, and it would be moving with the same velocity. So you get the same amplitude and the same velocity, but what you would get is a change in phase. That's really what happened here, is that this was a phase change. It basically got out of phase by 180 degrees, or pi radians. All right, so this is important to remember, because this is going to be a big deal, is that when it reflects, the reflection is out of phase. So it's pi radians out of phase. All right, so the question is why? Because it probably feels weird that it should get turned upside down.
Not really, because if you think about looking yourself in the mirror, it's a reflection of you in 180 degrees.
Okay, I can see that. Turns out that's a completely different reason. There's a completely different reason for that. But the fact that you can use that as you buy it. Well, here's how this plays out. The reason it gets flipped over is Newton's third law. Newton's third law, the good old, for a reaction, there's equal and opposite reaction. So think about what happens as this wave comes to the post. The wave, the string, it's trying to exert a force on the wall, right? What's it trying to do? It's trying to pull this post or wall upward. Well, that, of course, means that the wall is going to react by exerting a downward force on the string. So as that wave gets here, again, the string's trying to pull the post up, the post is pulling the string down. Well, the post can't move, but the string can. So then all of a sudden it starts pulling it down, and it keeps pulling it down until it's all pulled down and moving away. So it's actually good old Newton's law that makes that happen. All right, so in this case, reflection is exactly pi radians out of phase. However, what if we did the same thing? So here's our post. But this time, instead of it being attached, let's say that there's a little ring or hoop. And this ring or hoop is going to allow for the end of that string to go up and down. So you guys understand what I mean here? So this is our post. Got a ring around it, so it's free to move up or down. Okay, well, so now let's think about what's going to happen. If we go back to Newton's third law, well, actually this would be Newton's first law, right? As this string comes, this end wants to move up. And since it's not attached, it's allowed to move up. So as this comes in, the ring is going to move up. All right, so we're going to be up like that. And now we don't have that post or that wall trying to pull the string down. Instead, the string is going to just pull itself back down once the wave passes. So now what we're going to see is that that wave is exactly in phase.
Real quick, I don't really understand why the post wants to move up.
Well, in this example, it doesn't.
Okay.
In the second one, the post doesn't want to move up because it's not actually attached. In this first case, it did want to move up because the string, think about what the wave is doing. It's pulling the string up, right?
Oh, I see.
It moves, it's pulling the string up. So as we get right to the edge, it's trying to pull this string up. And since the string is attached, that means it's also trying to pull the post up. So it's trying to pull that pole up in that case. But over here, since it's not actually fixed, since it's just a ring, so it's loose on that end, then the post isn't getting affected and therefore isn't affecting the string.
That makes sense.
Okay. All right. So in this case, there is no out of phase, right? And here the reflection's actually in phase. All right. So clearly there's a difference between a wave being fixed at the end, at the reflection site, as opposed to it being free. So we call these boundary conditions because it's the condition at the edge, at the boundary. And this first one is what we call a fixed boundary condition. Because at the boundary, it's fixed. And the second one, we call this a free boundary condition. Because again, as it's moving towards there, it's free to do whatever. So this is going to matter. When you get to light, you're going to see that not all reflections are equal. There are going to be times when your light waves are out of phase and other times that they're in phase. And that's going to be super important when we look at things like what colors we see. For example, I'm not going to go too far in this because again, don't want to spoil, winter quarter for you next year. When there's oil on top of water, you get all the pretty colors, right? It looks like swirly rainbow. And that's actually because of the reflection of light coming from the top of the surface of oil and the bottom of the surface of oil. And so you definitely need to know how they're reflecting to determine what kind of colors you see. So just be aware that if there's a fixed boundary, and in the case of physical waves, what we're talking about, it's pretty easy to tell if it's fixed or not. Is it tied down, right? As opposed to the free where it's able to move up and down on its own. All right, so that's what happens with reflection. Now, another thing that we need to talk about when it comes to waves coming together is what we call interference. Okay, now interference, I know, usually means something bad. Like when we think of being interfered with, somebody interferes with us, or in football, right, there's an interference penalty. We usually think of it as it's a like obstruction, or it's it's a problem. That's not what necessarily is meant here. All right, when we talk about waves interfering, this is just when we have multiple waves that are interacting. So if we've got two waves that are just interacting with each other, they're traveling and they end up meeting, let's say, that's interference. So interference doesn't necessarily mean anything bad here. It just means that two waves are coming together. All right, so here's kind of the picture again. Let's say we've got a string and we're going to send two waves at each other. So maybe Max and I are on opposite sides of this string and we each give it a little bit of a pulse. So like, let's say this is mine and I'm sending it this way. And then maybe Max sends another one. I'm going to make it so that we can definitely see that there's a difference. So I'll make that one just shorter. Okay, so we've got these two waves coming together. So obviously, until the waves get to one another, we're going to see two distinct waves, the two independent ones that are moving. But the question is, what happens when they both get kind of in the center of this picture?
I think they're going to equalize and become one.
Okay, and
just
they do.
Going in opposite directions.
They definitely combine. They combine into one wave. So at some point in time, what we're going to see, I'll change the color because now it's not blue or purple because it's kind of a combo. And hopefully you can see that as taller because that was my intention here. We're going to actually see a larger wave when those two are together. And then a little bit later, they're going to separate back into two waves. And we're going to see, again, the larger one over here. and the shorter one on this side. But still moving in their original directions. They've just passed each other. So this is interference. So the question is, how do we figure out what that wave looks like? What do we get when we actually have those two waves passing each other? Well, what we get to use is what's called the principle of superposition.
It's not. Is it related to conservation of momentum and collisions?
A little bit. A little bit. The fact that we see the same waves afterwards is definitely a conservation of momentum. There's also conservation of energy here, because we don't lose energy when these waves come together. And that's where it's it's sort of like it's a elastic collision, but at the same time, there isn't a rebound. So it's similar, but a little bit different.
Is it like you never lose energy, or in specific situations?
Okay. There will be a little bit of loss of energy in a physical wave. Like if this was legitimately a string, there would be a little bit of loss of energy, because there's always a loss of energy as a wave is going on a string. Just because of like the deformation of the string and stuff like that. But if these were light, they would pass by each other as if they never saw each other.
Interesting.
So there are situations where it legit is energy conservation. And even those places where it's not, the loss of energy is really minimal with waves due to interference. So superpositioning, basically all this means is that you add the waves together. You take the functions that describe the waves.
Just like what we're doing? All the superpositioning in Diffie-Q?
Yep.
Okay.
Yeah, this one you actually can relate to what you're talking about in class. So same word, same meaning. So we can add the waves together to get their combined form. So if you could describe each one of these mathematically, if we could create a function that follows that linear wave equation. So we built that last time. It was the relationship between the second partials of x and t. So if we have something that follows that, so we describe these two with that, when they come together, you got this black one, we would literally just take their two equations and add them. Okay, so let me show you what happens if there are two sine waves, because those are the ones that we tend to like to look at because they happen a lot. But let's say we have two waves that are traveling that are sinusoidal, and the only thing that I'll make different is that they're out of phase. We'll allow for them to be out of phase. So let's say that y1 is a times the cosine of kx minus omega t. And then y2 is going to be a cosine kx minus omega t plus phi. So that just means that they're not necessarily in phase. If phi is 0, then they're exactly in phase, and so we're adding the same wave to itself. But that phi allows us to have variation. Okay, so then combined, we literally just add them. Whoops. Got the plus. And I'm going to put brackets around this because I can factor out an A from each. All right, so yay, we just added them together. But this is where we bring our trig back. Who'd have thought that trig would be useful here as well? I would have thought that. All right, so we have all kinds of identities. And one of them, it's called the sum to product identity. So for those of you who took trig with me, they were like the very last ones we saw after we had done sum and difference of angles and double angles and half angles and all that good stuff. We ended up with what we call sum to product identities. Okay, well, we're going to use those because clearly you can see we have a sum. We've got cosine plus cosine. So we can use the sum to product. So you can just take my word for this, or you can go back and figure it out yourself or look at them. But when you have cosine plus cosine, what you end up getting is 2 times the cosine of the average of these two. So you add them up and divide by 2. So we're going to get kx minus omega t plus phi over 2. Right, because you're going to get 2 kx's and 2 omega 2's. So when you divide those by 2, the 2 goes away. And then you also get the cosine of half the difference of them. Well, if we subtract one from the other, the kx and the omega t are going to go away. So all we're left with is the phi. And so we get cosine of phi over 2. So let me just rewrite this real quick. So we have y equals 2a cosine of phi over 2 times cosine of kx minus omega t plus phi over 2. So let me just circle that because I want to bring your attention to it. But this is what we're going to get if we combine 2 sine waves. If you had done sine and sine, you would have gotten something similar, except instead of this being a cosine, it would have been a sine. But regardless, I want you to notice a couple things. First, if you look at the wave bit, this is exactly the same period wave. It's got the same period, it's got the same wavelength, because it's got the same k and omega. It's just out of phase. And in fact, if you look at its phase change, it's exactly half of the phase difference originally. So it's in exactly the same amount out of phase with each of the 2 waves. All right, the other bit I want to draw your attention to is this. That's in green. And I know you're looking at that and going, oh, that's another wave. It's actually not. We do have cosine, but this phi over 2, that's just a number, right? Phi was how far out of phase these two were. So once you tell me how out of phase they are, I divide it by 2, and I put it in here, and I just get a number. So all of this, the 2a cosine of phi over 2, that's the amplitude of this combined wave. So let me just write something up here. So the amplitude of the combined wave is 2a cosine of phi over 2. Now, this cosine, you know cosine is trapped between plus and minus 1. So the biggest this could be is 2a. The largest we could get as an amplitude is if the cosine is equal to 1, and so we get an amplitude of 2a. So can you tell me what kind of phase difference would give me an amplitude of 1, or a cosine value of 1? What angles give you cosine of 1?
0.
So 0.
2 pi, pi and 2 pi.
Okay, so also pi, 2 pi, 3 pi, so some whole number of pi.
Yeah.
So we're going to get this biggest amplitude. This is going to occur when phi is some multiple of 2 pi. Right, because like if it's 0, obviously we get cosine of 0 is 1. If it's 2 pi, this is cosine of pi, which is -1. Okay, well that's fine. It's just inverted, but it's still going to be our biggest. Okay, so remember what phi is. That's how far are we out of phase. So if phi is 0, these things are not out of phase, which means the max of one is on top of the max of the other, because it's the same stupid wave. If phi is 2 pi, it's still the same situation, because a 2 pi phase difference just means you brought that max over to the other max. Same thing if it's 4 pi, we just shifted it 2 maxima over. 6 pi, it's 3 maxima, and so on. Okay, so we're going to get our biggest amplitude when these things are lined up max on top of max. I'm going to put here maxes with max. All right, well, let's think about when this is going to be smallest. What's the smallest number we could get for the amplitude?
-2a.
Okay, so -2a would be the smallest number on this, but remember the amplitude is the absolute value. So if we were at -2a, it's actually going to be the same in terms of amplitude of the final wave. It's just going to be upside down. Because I guess
So
technically it should be absolute values. So what's the smallest this would be if we accounted for the absolute value? So Ralph just said pi over 2. I think he's going with if this is equal to pi over 2. Because cosine of pi over 2 is 0. So the smallest we could get is actually 0. It's possible to put these two waves together so that we get a 0 amplitude result. Well,
But
if we've got 0 amplitude, that means that we have no wave. So in this case, they would actually cancel each other out. But Bradley, you were saying something?
If we had pi over 2, wouldn't we have negative 2a? Because the 2's would cancel, and then we'd just be left with cosine of pi?
If the entirety was pi over 2.
Got it. Got it. So, okay, that makes more sense now.
Yeah. So in this case, that's going to be where phi is equal to pi plus 2 pi n. Because if we plug in pi, we get cosine of pi over 2, which is 0. We plug in 3 pi, we get cosine of 3 pi over 2, which is also 0, and so on down the line. Okay, so what does that mean if they are out of phase by pi? What would that look like?
They're opposite signs of each other?
Yeah, so like one would be at a max, and the
And
other
the
would
other would
be
be
at
at
a
a
min.
min. Yeah.
So in this case, we've got a max with a min. So it's all about how are these two waves related to each other. And if we're at any other point, somewhere in between, we're going to get a different amplitude. That's somewhere between 0 and 2a. But think about these two extremes. This second one, the waves cancel each other. With the other one, check out what happened. The amplitude got doubled. And so I'm going to say that this is greatest how about building? Greatest of building happens here. And we actually get a wave that's twice as large as the original. Well, we have names for these situations. This one where it equals 0, we call this destructive interference. So remember, interference isn't necessarily bad, which is why we need to attach to it the name destructive, saying that those waves are canceling each other out. So you want to make a guess what we call the other one? What's the opposite of destructive? Yeah, Victor just threw it out there. It's constructive. So this one's constructive interference, meaning that they're actually building upon each other. All right, so the moral of the story here, if we've got sine waves, you take two sine waves, you combine them, you're going to get another sine wave with the same frequency, the same wave number, right? Everything is going to be the same there in terms of wavelength and all that. The only difference is it's going to potentially be out of phase, and the amplitude is going to be determined by that 2a cosine of phi over 2. All right. Well, remember when I was talking about needing to know about the phase change on reflection? This is why. Because if we're going to talk about, say, two light waves that are coming from reflections off of a surface of oil, for example, we need to know how out of phase they are so that we can determine what kind of amplitude we get when they construct or when they interfere. And we have to take into account that sometimes those reflections automatically give us a pi phase difference, which could potentially cancel it out. All right. Well, let's take a break because I'm going to set something up in here, and I'm going to see
Really quick.
if. I'm sorry. Go ahead.
Is that 2 pi r?
2 pi n.
Oh,
where
n. Okay.
N is just insert your favorite whole number.
Okay.
So we're going to take a quick break because I'm going to see if I can set up a demo. Okay, so we're going to go a little mobile here. We're going to take a little walk. I want to show you what I've got. A little walk means all of like 3 feet over to the side here. But I want to show you what I've got set up, and hopefully it will give you a good demonstration of this interference and constructive versus destructive. The other thing I just want to point out, because I've got my phone, I'm not going to be able to read chats very well. So if you have some comment, go ahead and throw it in verbally if you would. Just that way I'll actually hear it. So let me show you where we're heading here. Okay, so all I've got set up over here, it's pretty basic setup. It's not that crazy, but I've got 2 of these little boxes here. They are what we call function generators. They will basically create a sine wave or a version of a sine wave. Let me show you here real quick. You can kind of see we have some options of different kinds of waveforms. So you see one that looks like a regular old sine wave. The next one kind of looks triangular. Third one looks boxy. If I wanted to program something into a computer, I could send it in through those ports, but we're just going to go with the regular old sine wave. But it's going to create a sine wave. You'll notice over here, it's just going to give us a reading in hertz, and we can adjust what that looks like. So out of that box come a couple of cables, and you see that those cables then are attached over to this, and this is called a mechanical vibrator because it is mechanical and it vibrates. Yeah, you gotta love it. Okay, so it's mechanical vibrator, which really all it is, if you look at it from the side here, you can maybe see there's like a little brownish membrane in there, and that brownish membrane just goes up and down. There's a little post here that goes up and down, and so we'll be able to see it vibrate. So let me go ahead and turn this on. You'll probably hear some noise. All right, you guys all hear that?
Yeah, I heard it.
Yeah. Okay, so it's kind of like a high kind of buzzing noise.
Yeah.
That is the sound of 1,000 hertz. So let me adjust our frequency. So that's 500 hertz. So hopefully you hear a difference. This one's not nearly as high. Probably feels a little louder, but it's not as high in the pitch. Well, let me turn it down even more. Okay, so that's 250. That's what we hear, 250 hertz. All right, well, anyway, so that's how this is operating. If I really lower it, so this is 25 hertz, you may not be able to hear it, but what you can probably see is the top of that post. It's moving up and down. Let me slow it down even further. This is 9 hertz. I'll slow it down even more. So that's 6 hertz. So that's going up and down 6 times a second. So that's basically what's going on. It's just when it was up at like 500, you couldn't exactly see it because it was so fast. Okay, well, anyway, so that's the setup. I've got a second one. And what I'm going to do is I'm going to turn them both on and have them both be at the same frequency. Okay, so let's see how this works out. So I'm going to change this one back. I'm going to go to that.
Going.
What's that?
I think I might know where this is going.
Oh, well, so I'm creating two waves that have the same frequency. They're going to be potentially out of phase. Huh. All right. Well, okay. Well, let me get back to a good number here. I'm going to go to 500 because that seemed to work pretty well. So that one's at 500. Now let me turn the other one on. All right. Okay, they're both at 500. You can actually hear that they're exactly the same. If they're off a little bit, check this out. So for a little bit there, I had them off by 4 hertz, and you heard that like vibrating, that pulsing. We'll
Yeah, I
talk
heard
about
that.
that later. Those are beats. Okay, so these are both at 500. Now what I'm going to do is I'm going to move my phone around the room. Hopefully, wherever my speaker is going to move from places of constructive interference to places of destructive interference. And what you should hear is that the intensity of this sound should go up and down. There'll be places where it's louder, places where it's quieter. So I'm not sure if this will work. Never tried this before. I do know that if you walk around this room, like if I put my head in different places, I can hear it. But obviously you're not in my head. So let's see if this works. I'm just going to move my phone around. Okay, so I just turned them both off. But were you able to hear changes in loudness and quiet?
I noticed those changes, yeah.
Okay, so I'm getting lots of thumbs up. Good. Well, that's good to know that this works. I'm going to go ahead and get this set back up for a second. Well, no, not just yet. I'm going to do this. Okay, so what was going on as I was moving the phone and I was taking it to different locations is we were going from places where there was constructive interference. That's where it was loud. The way to think about sound, amplitude is loudness. So greater amplitude means louder sound. So when it was louder, we were at that place where the amplitude was 2A, where we were actually combining them. Where it got quieter, that's where the amplitude started dropping off because of destructive interference. Now, it's probably such that my microphone on this is too small for us to actually get it to a point where it's completely absent of sound, because even just a little bit of a distance will make it so that we're not completely out of phase. And so there still will be sound, and especially like a cell phone microphone are really, really good at picking up sounds. So, and the same thing if you're wandering around the room because your ears are on opposite sides of your head and there's distance, you'll still hear some sound, but it gets quieter because at least it's partially getting destructively interfered. So I'm glad that kind of worked out, because that's a demo I love to do in class just so that you guys can actually see it. So before I go and sit down, anything you want me to experiment with these sounds real quick? Because I don't mind. Okay, I'm hearing nothing. So I'm going to go ahead and get this back and have a seat, and we'll get back to kind of usual. Okay, so I'm back. So kind of interesting, right? That we can actually experience that. We can see, or hear in that case, physical evidence of constructive and destructive interference. Turns out we see the same thing with light, that you can get light that cancels itself out. And so you can get light spots and dark spots. When you get to optics, so in fourth quarter, you'll see how you can do this. You need to have light that is the same frequency, meaning the same color. And it really works out well when you use lasers, because lasers are specifically one wavelength, one frequency. So you'll see with lasers, whether it's me or Kathy, who knows who that'll be at that point. But you'll see how we can create this pattern of constructive and destructive interference as we go. So let me kind of show you on the board kind of a map of what was happening here with sound. So let me draw this picture. We're going to have those two speakers as point sources. So here is speaker number 1, and it was sending out waves that were coming out spherical. Now we're just looking at this from the side, so it's just 2-dimensional, but in the real world it was 3D, right? There were spheres coming out. So there was speaker number 1, and then speaker number 2 was over here somewhere doing the same thing. My brown one is much more concentric than my purple, but we'll call it good. Okay, so here's where we had these two creating the spheres. Now, where those spheres met, that was constructive interference. So if we look at these intersection points, so let's make some X's on some of them. I'm going to do all of them. But like at all of those places, we had constructive interference. Think of those circles as locations of the maxima. And so we saw that we got constructive interference when maxes were with maxes. But it turns out you also will get that constructive interference where mins are with mins. Because if minima are together, it's the same as maxima. So we're also going to get constructive interference at the midpoints, the places where we're exactly halfway between each of them. Okay, so there are some more spots where we're going to get constructive interference. So all those red X's are constructive interference. Well, now let me put blue where we have destructive. So destructive is going to be where there's a maximum of one with a minimum of the other. So on this picture, it's going to be where one of the lines is in between two of the other color lines. So destructive, I'll make these dots too, they'll be blue dots. Destructive interference are going to occur at these locations where we're on one of the circles for one of the colors, but we're exactly halfway in between the circles on the other. So notice how they are all intermixed. There are some red ones here, but then there's a blue one, there's a blue one. And so as I was moving my phone around, I was going from loud spot to quiet spot to loud spot. And so that's why you were able to hear that even over a short distance. Anyway, so interference is real. It's definitely real. We know it's real because we can experience it. All right. So interference does a lot for us. There are a lot of things that happen, not just what I was talking about here. And another big one is what we call standing waves. So let's talk about those. Now I'm going to talk about these as standing waves on a string, but they can occur in any medium. And we'll see that when we talk about sound, that we can get standing waves there as well. But here's how this is going to play out. So we're going to have a string, and that string is going to be fixed at one end. And what we're going to do is we're going to vibrate the other end up and down. So we're basically going to create a sinusoidal wave. Okay, so we start sending it, and we start sending a wave. So let's just look at a time-lapse picture. We're just going to take a picture at some point, and let's just say we sent one wave. But what we would see, let's say maybe that's the one wave that's going in this direction. So what's going to happen to that wave when it hits over here? What's it going to do?
If the point at the end doesn't move, it'll go backwards, opposite.
Okay, good. Yeah, and it is fixed. I want it to be fixed. But it's going to come back completely out of phase. Right? It's going to come back so that this red is now going to be on the return trip. The return trip, this thing's going to get flipped over. So, well, let's just think about it this way. So this first bit that was down below, it's going to start by going up, and then more of it's going to go up, and then more of it's going to go up. But eventually, it's going to be coming back, and let's just say this is on our way back. But now we've got that pulse coming back. All right, so we're going to create interference. We're going to now have the wave that we're sending down interfering with the one that's getting reflected. So just by the nature of this reflection, we're going to create interference. Okay, so the question is, what does it become and what does it look like? Well, let's actually just go to the math. Let's take the equations for these two waves and let's see what we get. All right, so the one that's traveling to the left, the black one, let's say that we'll call that Y1. So it's going to have a given amplitude, whatever amplitude we're setting. And then we're going to have a sine of kx minus omega t. Okay. Because it's moving to the left.
Is there a reason you
Sorry,
chose sine instead of cosine?
No, just because I felt like it.
Okay.
Remember, sine versus cosine doesn't really matter. Would you prefer cosine? I don't mind.
No, I was just curious.
Okay. So now let's think about the one that comes back. This is going to be Y2. So first of all, we know it gets inverted. because it flips over. That's how we're going to do the phase difference. Instead of adding a pi or subtracting a pi, we're just going to put a minus out front, meaning it got flipped over. Okay, now it's traveling the opposite direction. Which means we need to change the sign on the k of x. Sorry, I changed the sign on the wrong piece. All right, so literally what we're going to do is we're going to add these two things together. So I just want to remind you, be a little bit careful here, because you might go, okay, cool, the kx and the minus kx cancel and all that. It doesn't work out that way. We have to be really careful with the fact that if we're adding sine functions, we got to go back to that sum to product identity. But basically, let me just jump to the result for you. The result of this is that we're going to get a resultant function of 2a times the sine of kx times the cosine of omega t. So if you use the identities, this is what you're going to get. All right, so I want you to notice a couple of things. First, just like last time, when we added two sine waves, you notice that we are getting a 2a, not a surprise, right? Best case scenario is we literally get them on top of each other, so our amplitude is twice what we started with, right? And then notice that this is a little bit different. It's still similar where we've got a sine times a cosine, but now neither one of these is constant. When we did it before, remember how we got that cosine of phi over 2? And that was just a constant. That just told us how out of phase they were, so what kind of amplitude we got when we added them together. Now we don't have that. We still have two trig functions. We've got a sine and a cosine, but notice that one of them, the sine, this depends on position. So I'm going to put location. So depending upon where we are on the string will affect what kind of amplitude we have. The other part, the cosine, that one depends on time. So basically, what we're going to get is a wave that's on our string whose amplitude depends on where we are and when we're at that point. So if we were to choose a location somewhere on that string, it's still going to be moving with time. It's still going to be going up and down with time. Just like if we were to pick a time, we'll see that the height depends upon where we are. So kind of crazy. But this is purely because of the fact that we're getting this reflection coming back. Okay, so let's look at this location thing, and let's look at that sine. So if we really wanted to look at this in terms of what's happening at any one place, then the 2A sine, this is the amplitude of the oscillation. So you tell me where we are, you give me an X number, I plug that in, and what I'm going to get is the amplitude of my oscillation. So how far are we going to be going up and down at that location? So does that make sense what I'm saying here? The amplitude of the oscillation at the location. So you pick a place, and then once you pick that place, that will tell you how far you're going to be going up and down.
Yeah, that does make sense.
Okay. All right. So let's look at that for a second. This guy, 2A sine of kx, that's going to vary. Just like before, we're going to see that this amplitude is going to be between 2A and 0. So there are going to be places where the string is not going up and down. And there are also going to be other places where the string is going up and down as much as we possibly can. So let's see if we can figure out where that would be. So if we want the amplitude to equal 0, right? So we're going to go with this lowest case. That's going to be when the sine of kx equals 0. Well, that'll be where kx is equal to some multiple of pi. And so from that, we get that x is equal to n pi over k. But we can go a little bit further. K has to do with the wavelength. It's 2 pi over lambda. So let me just remind you, we saw this, I think we saw this last time. It might have been the time before. But we know that the wave number is equal to 2 pi over lambda. So let's go ahead and put that in. So if we put that in for k, the pi's cancel, and we get n times lambda over 2. And so this is the big result. If you look at these places, notice that they are all multiples of half the wavelength. So if we were to make the list of places where we're going to get 0 amplitude, that list would start with 0, then 1/2 lambda, lambda, 3/2 lambda, 2 lambda, and so on down the line. So they are regularly spaced. They're occurring every half wavelength. All right, well, that's where our amplitude is equal to 0. It's at every half wavelength. If we look at the flip side, where is our amplitude greatest? So we go to amplitude equaling 2a. This is where sine of kx equals plus or minus 1, which will be where kx is equal to the half pi's. So 2n plus 1 times pi over 2. And we do the exact same thing where we do the whole 2 pi over lambda and whatnot. And what we're going to get there is 2n plus 1 over 4 times lambda. And I know that when it's written this way, it doesn't really tell you much. So let's write out the values. So this set of x's, if n is 0, the first one is lambda over 4, so 1/4 lambda. When we go to 1, we get 3/4 lambda, 5/4 lambda, 7/4 lambda, and so on down the line. And notice that these are exactly halfway between the others. So if we were to look at any two places where we get no amplitude, there's going to be a spot exactly halfway in between that has maximum amplitude. So there's this alternating set of things that are 0 amplitude and max amplitude. So let's take a look at that. Let's draw this wave again. So think about what we're going to end up with now. So this is the resultant wave, right? So we've got our string, and let's just say that this is x equals 0. So already what we know is that 0 is going to be a place where we do not go up or down. I just erased it, but that was on our list of places where we get no amplitude. So somewhere down the line, a little bit further, is going to be a point right here that's at x equals lambda over 2. And then there's another point over here that's x equals lambda. And I'll do one more just for good measure. But those were the first 4 on our list of places where we got no amplitude. So that means that as time goes on, these points do not move. Because remember, amplitude is up and down. These things are not moving. Now, exactly halfway between these are going to be spots. Let me just mark them here. So this is the 1/4 lambda, 3/4 lambda, 5/4 lambda. And think about what's happening there. These are oscillating back and forth. And they're going from positive 2A to negative 2A. So let's say that that's 2A and this is minus 2A. So this piece of the string is bouncing back and forth. It's moving back and forth between these. Similarly, this next spot, we see the same thing. It's just cruising back and forth between those 2A and minus 2A, so on and so forth. Now, if you were to look at any other point, somewhere not at these, you will see that there is an amplitude. It's not going to be 2A. It's not going to be 0. It's going to be somewhere in between. So like, let's say we're looking right here. We're going to see that oscillate, but it's not going to oscillate as far. And maybe we look at another point over here that gets close to that point of 0 amplitude, and we see that it bounces back and forth, but on a much shorter one. And then maybe there's another point that's kind of close to one of these great extremes, and so it will go up and down a lot, but not quite as much. So what I'm drawing again with this arrow back and forth is showing where this piece of string is going to be. It's going to bounce back and forth between these two locations. So sometimes it's up top, sometimes it's down at the bottom, and it travels from being up top to down at the bottom and then back and forth and back and forth. All right, well, if you kind of connect the dots, you're going to get like a little bit of an envelope here that shows you where the string is. And then we're going to see another one down here. And yet another for this next set, and so on and so forth. So we'll see as many of these as we can have for our length of string, right? How many we have is going to totally depend on what the wavelength of the wave is and the length of the string. Well, this is what we call a standing wave, because we basically have one wave. Let me show it to you. It's right here. Okay, so you see that blue? That is our wave. The only thing that's happening with that wave is it's moving up and down. And so that's what we call our standing wave. So some terminology for you in our standing wave. Oh, and what you would see, and I'm going to try to get this set up for Monday. I think I forgot one of the pieces at the college, but I think I can improvise, but we'll see. But what you would actually see is it would look fuzzy. When you're looking at this, it would actually look fuzzy because you're seeing that string occupy all that space at different times. So it's going to look fuzzy. But these points are going to look like they don't move at all. All right, so names for these things. The points where our amplitude is 0, we call those nodes. Okay, so a node, this is where the amplitude is equal to 0. So think of it as these are the points that don't move. So on this picture, it's the red dots. Okay, so this is a node. There's a second node, a third node, a fourth node. So on this picture, I have 4 nodes that are drawn. But again, you're going to have as many of them as the length of the string allows for the wavelength. So I'm just going to write an N over where the nodes are. Okay, so those were our nodes. The places where amplitude is greatest, where we're moving furthest, we call those antinodes. And this is where we're going to get an amplitude of, not 2 pi, 2a. And I was going to
really creative name.
Yeah, I know, right? It is a shame that we as mathematicians and scientists are that lame. But it also makes it easier to remember things, right? Because, okay, you got a node, and then the other one's an antinode. Cool. Continuous, discontinuous. But yes, antinode, yay. So antinodes, those are going to be the places that have the greatest movement. And so that's these black dots. So I'll put an A over where the antinodes are located. So we've got nodes, we've got antinodes, and they alternate. And they literally just alternate every quarter of a wavelength. So if you know the wavelength, you know where these things are going to be, and you'll know how many of them you get if you know how long your string is. All right. So yeah, there you go. That's what a standing wave looks like. But standing waves are huge. Let me come back here for a second. So standing waves are a big deal because this is why like musical instruments work. So think about like a guitar, and this is true for any stringed instrument. So whether it's a guitar, a piano, I know you don't think of a piano as a stringed instrument, but there are strings in the, back behind that get plucked when you hit the keys. But so guitar, piano, violin, you name it, anything that's got a string. So here's why certain notes play. It's because of the standing waves. So we send a wave down by strumming the guitar, playing the bow over the violin, actually plunking down on that wire with the hammer from a piano. That sends a wave down the string. It comes back and creates a standing wave. It's what we call resonance. Remember, we talked about resonance a little bit with simple harmonic motion. It's the same deal, right? So resonance means that they're building upon each other. So you get that resonance, and then you get to hear the sound. Now, the sound that you hear depends on the frequency. Remember on that box that when I was showing you interference, you change the frequency, you change the sound. Well, frequency is related to wavelength. So basically, you can think a certain frequency means certain wavelength. Well, they construct those strings such that you can get a whole number of wavelengths traveling on your string so that you can get a standing wave. Now, the other thing that comes into play is not just the length. Like if you look at a piano, if you take apart a piano, you'll see that all the lengths are different. They have different length strings. But like a guitar, they're fixed length. So the way that we get a different sound on those is by changing the tension. So I don't know if anybody's ever played guitar, but the way you tune a guitar is you twist the knobs that are out on the very end. And what you're doing there is you're changing the tension on the wire, on the string. So that change in tension changes how fast the waves move. Hopefully you remember that from our discussion last time, right? That the speed depends upon, on a string, it's tension over mass density. So you change the tension, you change the velocity. If you change how quickly these things move, these waves move, you will change the frequency for the set standing wave. So if it weren't for standing waves and constructive and interference, we wouldn't have music. And it turns out that we get similar things when we look at music that happens in a wind instrument. It's a different kind of wave, and we'll have to talk about where interference happens because it forms a little bit different. But the same thing happens so that when we blow a note through a trumpet, right? When we blow air through a trumpet, we get a certain sound. And that's all, again, due to standing waves. Okay, so let's end our discussion today. I do have a little bit more I want to do, but let's talk about how we can figure out where those, or what the frequency would be for a standing wave on a string, depending on tension and all that good stuff. So let's go back to the board. All right, so let's think about what we're going to need to get a standing wave. And we're going to start with the easiest, most basic standing wave on a string. And that's going to be one where we get only one antinode. So the two ends are going to be nodes, and we're going to get an antinode inside. All right, so this is pretty boring, right? No question about it. It's pretty boring. But this is the first one that we could get. This is the first frequency we could get for this string. So let's give it a length. let's just say that it's a length of big L, the length of our string. And so what we know in this case is that that length is actually equal to 1/2 of a wavelength. So I just said that like with firm confidence. We know that. Are you convinced?
Yeah, because we don't have a minimum.
Yeah, and remember where those nodes are? Those nodes happen at all the half wavelengths. So the first one's at 0. The next one will be at 1/2 a wavelength. That just is from what we calculated on the last, when we did that thing before. Okay, so in terms of what that wavelength is then, that wavelength is 2L. So that would be best, easiest case, right? First case. All right, now, the next one we could see, we've got that same length, is one where the end is actually the third node, not the second. So we've got nodes at the ends, but if that's the third one, then there has to be another one exactly in between. And what we would see is a standing wave that looks like this. So we've got 3 nodes and 2 antinodes. Well, we do kind of the same thing now. We know that the length of this is actually equal to just L. That entirety is 1 wavelength. So that L is 1 lambda. So L is equal to lambda. So let's do one more and maybe we'll see a pattern. Right here, this lambda was 2L. The next one, lambda was 1L. Let's see if we go to the next case. So this time we need 4 nodes. So it's going to look like that. So in terms of what we see, we'd see this kind of pattern. And if I can get this for you guys on Monday, this picture will make a lot more sense if I can actually show you one, because then you'll go, oh, yeah. Okay, well, let's think about this then. This time, L is going to equal 3/2 lambda. So lambda is equal to 2/3 L. So notice that the wavelength is getting smaller. It was 2L, then it became 1L, then it became 2/3 L. And what we'd really love is to have some sort of a formula for the different possible lambdas, right? Like what are the different lambdas that we get depending upon which stage we're in. So let's go to generic. If we go to a generic one now, I'm going to leave that number of lambda equals 2L up there, but let's go to a generic. So here's our length, and we know we've got nodes at the 2 ends, and then we've got a certain number of other nodes. But we know that this length, it has to equal some half number of wavelengths. All right, that's what we actually calculated when we were looking at the superpositioning. Well, if we solve that for lambda, we get lambda is equal to 2L over N. And so these are the different possible wavelengths we can have on a fixed length string in order to have a standing wave. It's going to be 2L divided by N. So you can see where these came from. This was 2L divided by 1, 2L divided by 2, 2L divided by 3. So the next one's going to be lambda equals 2L divided by 4. So half the length. Next one's going to be 2/5 the length, then 1/3, 2/6, and then 2/7, and then 2/8, or 1/4, and so on and so forth. All right, so this is cool. We definitely know the possible allowed wavelengths, but we probably would rather look at those in terms of frequency. So let's see if we can figure out the frequencies of these things. So do you remember how frequency and wavelength were related? This is something we also would have talked about either Monday or Friday. I don't really remember when. So I'm going to take that as a no. That's all good. Okay, so the way that frequency and wavelength are related is through speed. What we know is that this wave speed, it's actually equal to frequency times wavelength. And you can see that the units work out here. Frequency is per seconds. Wavelengths are meters, so we get meters per second. So frequency then is equal to our wave speed divided by lambda. So let's look at the different possible frequencies we can get. So all we got to do is plug this lambda in for that into this formula. So we're going to get potential frequencies of V over 2L over N, or V over 2L times N if you invert and multiply. So these are our potential frequencies. And that's going to correspond to the sound that you hear. So again, kind of check out how we could change the frequency, change the sound. We can change the L, so you can change the length of the string. Well, that's why in like a piano, some strings are long and some strings are short. We can also change it by changing the speed. So Victor, that's a 2L, not a 2 lambda. So that's the length of the string.
So real quick,
Yeah.
you know how you said the units of frequency are per second?
Yep, they're hertz.
I can't really wrap my head around a per second. Like, what is that?
Okay, so it's how many happen in 1 second.
And that's like, trying to think of the word. How many? I don't want to say cycles, but
Yeah, that's fine. We can
cycles
talk about
work.
cycles per second.
Okay. I
Right,
guess
so,
if we put it in trig terms, rotations.
sure.
Okay.
Yeah, so
All right.
you know frequency as like angular velocity, angular frequency, which in a circle, like in trig terms, is exactly what you're talking about. It's like how many times do we go around every second? But hertz are allowed for anything that is regularly occurring, right? And so this could be if I clap my hands, all right? So if I go, there's a frequency. That frequency would be how many times does the clap happen in 1 second?
Okay.
Or in the case of a wave, it'd be how many times does a wave go by in a second? Or in the case of a standing wave, how many times does it oscillate? Because remember, we got, like, think about an antinode that's going from top to bottom, just bouncing back and forth, right? The frequency would be how many times does it go from top and return back in 1 second? And so when you said cycles, I think that's very, I mean, that's a great word, because if we're at the top, 1 cycle would be down and back. And so frequency is a measure of how many of those happen in 1 second.
Okay.
Okay, so time, we're timing how long it takes for something to get back to where it was, as opposed to frequency is how many times does it go back and forth in a set amount of time. So it's just the reverse. We're just flipping our thought process.
Okay.
Does
Because
that
at
help you?
first, yes, because at first, like, a meter per second makes sense. You go however many meters per how much time, where it was per second, so I was hard, like,
Yeah.
grasping that. But that makes complete sense.
So
Thank
just
you.
replace the meters with something that doesn't have a unit, right? Because like when you talked about speed, and you go 10 meters per second, it means you traveled 10 of those things in 1 second. We just call those meters. But it's still kind of a frequency, right? Now it'd be there are 10 claps per second. There are 10 cycles per second. There are 10 meters per second. It's just what we're measuring isn't length. What we're measuring has no unit. It's specific, I mean, it's literally just a quantity. Count up how many times I clapped. Count up how many times you saw that thing go by. Count up how often or how many times it went from top to bottom and back. Right? So in this case, it's when we just count something, and we're looking at a count per time, that'll be hertz. Anyway, so hopefully you feel better.
Definitely. Thank you.
Okay. And if you still have confusion or you want to talk more about it, just let me know sometime, Bradley, and we can chat on office hour or something else. All right, so again, we can change that frequency by changing length, but we can also change it by changing the speed of the wave on the string. And what we saw last time is that that wave speed depends upon mass, so the mass density of the string, and it also depended upon the tension. Yeah, kind of remember that? So what we saw before when we were talking about the speed on a string, so the speed of a wave on a string, was that V was the square root of the tension over the mass density. So the other way that we can change the frequency of a standing wave, frequency that we're going to hear when that thing gets struck and gets into resonance, is by adjusting either the tension or the mass density. So we can make it a heavier string or a lighter string, and we can also adjust the tension. So when you tune a guitar, you primarily are changing the tension. Well, when you tune a guitar, you are changing the tension, which then changes the velocity, which then changes the frequency that we're hearing, which means it's changing the sound. But it can also be accomplished with different mu. Again, if you look at piano strings, some of them are really thick and some of them are really, really thin. They're changing the mass density. And if you play guitar, you know that not all strings are created equal. Sometimes you use thicker, heavier strings, and you do that when you want to get lower notes, because they tend to give you slower velocity, which gives you lower frequency, which are quote unquote lower notes. All right, so we actually can tell a lot then about what kind of standing waves we can get and what frequencies we can hear. But here's what's kind of interesting. Notice that it's not just one specific frequency. There are a whole bunch for any one string, right? You give me a string with a given tension and mass density and length. All of this V over 2L, that thing's constant, but I can change my N. I can make N 1, 2, 3, 4. I could make it 5 billion even, which would give me a different frequency that I'm going to experience. Well, this one, the V over 2L, we call this the fundamental frequency. So we're going to write that as F sub 1. That's our fundamental frequency. And it's V over 2L, right? Or if you want to include that tension and mu, right? So either way you want to think about it. But that is your fundamental frequency. All the other ones are what we call harmonics. Okay, so the rest, we call them harmonics. Another word you'll sometimes hear are overtones. So that's kind of more the musical name for them. But harmonics are overtones. And again, just notice that they are multiples of this fundamental frequency. Okay, they're just going to be F equals N times F1. So hopefully, in addition to me showing you standing waves, hopefully I have the stuff to set up a lab where we can actually play with changing tensions so that we change speeds, so that we change fundamental frequencies, so that we see different patterns on the standing wave for a given length. So if I can rig it, which I probably can, we'll do that not on Friday, but the following Friday, because this Friday, we're going to do a lab on buoyancy, on Archimedes' principle. And we'll look and see if you guys can figure out mystery metals. I'll have some mystery metals, and I'm going to see if we can figure out what they are by looking at their density. All right, so any last questions on the standing waves on the string?
I just want to be clear, standing waves are different than just normal waves, correct?
Yes, because in essence, they're not moving.
Okay.
What's happening is they're just stationary. So when I say not moving, when we think of waves moving, as they move along the string. Now, they're not moving along the string. A fixed point is going up and down, but it's not moving along the string. But good question. Okay, well, let me pause the recording.